Multivariable calculus, we're looking at lesson 15.2, iterated integrals, definite double integrals. You can see our learning target at the top. I can evaluate double integrals. And this is one of the most mechanical lessons we're going to have in this chapter, which I hope is going to be really good news. What you do for a double integral, we're not going to approximate them like we did before. We're going to find the real true value. As you look at the integrand, of course, there's x squared y. But right next to the y, the innermost differential is a dy. That means we'll integrate with respect to y. The most inside integral is having bounds of 1 to 2. Those are y values. So let's take our antiderivative of y with respect to y, and this is going to be, and notice what I'm going to do, I'll just recopy this outside integral. But what's the antiderivative of x squared y with respect to y? Well, it's x squared is your constant, then we'll get y squared all over 2. And then we're just doing the fundamental theorem here. Look at that. So it's like I had said, a very mechanical process here. It's actually a very nice lesson where you just go through 2 steps. First, you'll take your integral with respect to that innermost differential with respect to that and use your fundamental theorem. So we're going to plug that 2 in for our y, and you can see that that's going to be, and by the way, if you'd like to pull the x squared over 2 out, that could be a very smart thing to do. Plug in a 2 just into the y squared, you'd get 2 squared minus a 1 squared. And we all know that that's really a 4 minus 1, which is a 3. So this is going to be the integral from 0 to 3 of a 3x squared all over 2 dx. And guys, at this point, this is a review problem from last year right now. Now we just use the fundamental theorem. We're going to bump this power up by 1 to a 3 because we're going to integrate with respect to x. We're going to divide by a 3. And so that 3 out in front is going to cancel. And guys, we mentioned this last year a ton too. You can always double check if you've done this right by taking your derivative, making sure you took your antiderivative correctly. Let's just finish this up. We'd have 3 cubed minus 0 cubed. So that's 27 minus 0. Final answer is 27 over 2. And we are done. As we come over here to part B, you're going to see it's really the same type of problem, except now we integrate first with respect to x. And that's super important for us to remember. The innermost differential tells you what to do. So as we take our antiderivative of x squared y, we'll get x to the third, treating y as a constant, all over a 3, and we're going to use our fundamental theorem. Don't forget this outer integral goes from 1 to 2, and that's with a dy. So hopefully you can see what we're doing. We're just going to plug that 3 in. By the way, once again, you can pull a y over 3 out. That's your constant. Then you'd have 3 cubed minus 0 cubed. And we all know that 3 cubed is 27. And the 3 cancels with the 27, giving us just a 9. So we're just going to be left with a 9y, and we're going to integrate from 1 to 2 of dy here. Now what? Now it's like an old school problem. Antiderivative, bump this up to y squared, divide by 2. And just finish with the fundamental theorem. Plug in your 2 here, you'd get 2 squared minus 1 squared. That's a 4 minus 1, which is a 3. 3 times 9 halves is 27 halves. So you can definitely work these out. Like I said, an extremely mechanical process. Here it says the volume of a prism bounded by r below and some surface up above is given by this. When you see this integral, you're saying, look, we're integrating with our x and y over a rectangular base. That's super, super, super important. So if your base is a rectangular region, and today it will be, what you're about to see, this is so very, very important. You can see that your volume can be accomplished by going in either direction. You can integrate first with respect to x or first with respect to y. You're going to get the same answer. What that's really called officially is Fubini's theorem. Fubini's theorem says, hey, if you've got a rectangular region, that's the caveat. We're assuming that we've got this rectangular region where x is bound between two numbers, y is bound between two numbers, and you've got some function of two variables in the integrand. It doesn't matter what you integrate with respect to first, you'll get the same answer. So as we take a look at example 2, just want to tell you, you are completely at liberty to integrate with respect to either of these variables first. Sometimes it's smarter to integrate with respect to one of the variables first. Looking at your integrand, x minus 3y squared, really taking antiderivatives here, it really won't matter, will it? If you'd like to go dy first, you may. Dx is bound between 0 and 2. Dy, let me erase that, is going to go between 1 and 2. You'd get the same answer either way, and honestly, it's really to no advantage to go with one variable first as opposed to the other. But let's go ahead and just integrate with respect to x first in here. So we'll get x squared all over a 2 minus a 3xy squared, and we're going to integrate between 2 and 0. And then we'll have to integrate finally in a latter step with respect to y. But first, we've got to finish this innermost problem. Let's do the fundamental theorem here. You can plug in your 2. You'd get 2 squared all over 2 minus a 3 times 2 times y squared. And then, of course, we'd plug in a 0 for both x's. I think you can quickly see what's happening. Well, inside, this is 4 all over 2, which is just going to be a 2. This is going to be a 6y squared. So as we continue, we'll have 2 minus 6y squared. And now it's like an old problem. In fact, it's something like you saw in Calc BC. Go ahead and use your fundamental theorem, integrating with respect to y, antiderivatives. Bump this up to a 3 and divide by a 3. And you have this. Once again, it only takes a moment to confirm that you've taken antiderivatives correctly by taking a derivative. Can't stress that enough. It only takes you a moment to do that. Really strongly suggest that. It's so frustrating to get a silly mistake when you just do something wrong arithmetically. Well, take a look here. 2 times 2 is a 4. 2 cubed is 8. 8 times 2, that's a 16. Inside here, we'd have a 2, and 1 cubed is 1, so this would just be a minus 2. 2 minus 2 is a 0. 4 minus 16, we're just going to get a negative 12, and that's our final answer. Guys, as you look at number 3, like we said before, this notation, this R stands for a rectangle. It's a rectangular base. And just want to tell you that when they give you the parameters for R, when they're saying that R is a rectangle that goes 1 by 2, cross that with 0 to pi, those are x and y values. X always comes first. So what we're really told is x is between 1 and 2. Y is between 0 and pi. Right now as we're looking at this, you can think, well, does it matter what we integrate with respect to first? And here I would argue, yes, it does. Look at this integrand. There is a y multiplied to the sine of xy. There are two y's here. Integrating with respect to y first could be problematic. It could be rather difficult. So let's go ahead and integrate with respect to x first. It's easier to do that antiderivative. And our x boundaries go from 1 to 2. Our y boundaries go between 0 and pi. So we focus in here first, an easier problem, and hopefully that will lead to an overall easier problem. Treating x as our variable at play, antiderivative of the sine is negative cosine. So we'll have our negative right here. Y is a constant. We'll have our cosine of, xy. But then we have to reverse the chain rule. You see, if we were taking a derivative of the inside with respect to x, we would have the multiplication inside after a derivative. The derivative of xy would just be a y. So we actually have to reverse that. We're going to divide by that. And then we'll finish with that fundamental theorem. So you can see where we're benefiting, where we're getting some help already. These y's are going to cancel out. And my goodness, now we can finish up this fundamental theorem. As we plug in our 2, and we can leave this negative out in front, and remember we're plugging it in for x, we'd get the cosine of 2y minus, and then when we plug in our 1 for x, we'd get the cosine of y. And thankfully, just as we had hoped, we actually are getting an easier problem to work with. We're going to distribute this negative in. Both signs are going to change. So you could write this as a positive cosine of y. That thing turns positive. We have a minus cosine of 2y right here. And now we just have to take our antiderivatives. Antiderivative of the cosine of y is the sine of y. And the antiderivative of the cosine of 2y would be the sine of 2y, but we have to reverse the chain rule. We have to divide by 2. And then we're going to plug in our bounds. So we'll have the sine of pi minus the sine of 2 pi all over a 2 minus, well, we'll have the sine of 0 minus the sine of 0 all over 2. Guys, just real quickly, I hope you notice that all of these values of sine are going to be 0. The sine of pi is 0. The sine of 2 pi is 0. Sine of 0 is 0. Final answer right here is actually just a 0. So in other words, we're seeing that, we can interpret this as volume. You can interpret this as net volume, much the way we did in Calc BC. Double integrals can be negative, of course. Z values can sink below the XY plane. Speaking of that, as we're looking at example 4, and the video is running out, I don't think we're going to be able to completely finish this problem in our time remaining, but we can definitely begin to see what's going on. Find the volume bounded by this elliptic paraboloid. Well, if we solved for z, it would only take a moment to see that you have this. And guys, you don't have to graph this. You certainly don't have to graph this. We did graph this way back earlier in the year. But an elliptic paraboloid, I think you could see if x and y were both 0, z would be 16. It kind of looks like this three-dimensional parabola, almost looking like a gumdrop, but where a cross-section would be an ellipse rather than a circle. So it would look something like that. But it's saying find that volume of this paraboloid bounded by the planes x equals 2, y equals 2, and the 3 coordinate planes. Well, just want to real quickly show you what would happen. If you had x equals 2 right here, if you had y equals 2 right here, of course we would have some planes going through those. And what's happening is then with the coordinate planes, that would be x equals 0, y equals 0, and